The last concept we're looking at in simple forces is called torque. Torque is symbolized with the Greek letter tau and is defined as an applied force on a lever arm that attempts to rotate a system. So here we're dealing with rotation as opposed to linear acceleration. The lever arm is defined as a radial extension fixed at the axis within a system. And so basically the lever arm is the radius of the system. So if we had a round object like this and we wish to turn it, if we had the radius out like this, this is your torque arm or your lever arm. In order to in order to rotate this system, we must apply a force at the perimeter of the circle in order to make this rotate. Now, the challenge is understanding that if we were to apply a force this way, not all of that force causes radial rotation, right? This vector is actually component-wise applying two forces, one that is parallel to the radius and pulling essentially outward, and one that is perpendicular to that, pulling down. So if we imagine that if we wanted this system to rotate clockwise and spin this way, the applied force is not actually this entire magnitude force, it is just this perpendicular component. So if we were given, for example, an angle theta, we could identify the torque as being the applied force out here, F sine theta, times the radius. So generally, torque will often be listed in that format, R times F times the sine of theta. This is a generic format and it only holds true when the angle given is this angle given here as theta. I tend to shy away from this because there's no guarantee it will be the sine function. It's absolutely possible they could give you a different angle and it would have to be the cosine, etc. What's more true is that torque, an applied force on a lever arm, is the radial arm which is perpendicular to the applied force. This is the proper format for the torque formula, where R and F are perpendicular. If the force and the torque arm are not perpendicular, then not all of the force is creating a torque. And so we often have to identify that first. So if I were to redraw this radial arm, R, this force, right, perpendicular, is what generates the rotation around the system that would cause this to then turn in that fashion. Most of the time you will see round objects, but it's not unusual to see singular planks fixed at one point that rotate. The most common example is a door. The door has hinges here at the fulcrum or the pivot point in the middle. That door extends out where the handle is. When you pull on the door, you pull perpendicular to the door with an applied force that then causes the door to rotate. You can imagine that if the door were semi-open and moved to some location here where this is still fixed out at the end and this is still your radius, if I continue to pull in the downward direction, then I'm losing torque because I'm essentially pulling more and more along this direction parallel to the radius. So as we do this instinctively when we open doors, we tend to rotate this force more and more this direction in order to continue to open the door. Since torque is applied force times a radial lever arm, the units don't have a defined characteristic besides the fundamental SI units of the system. So force is measured in newtons, radius is measured in meters, the units of torque are Newton meters. Besides your most basic problems of turning knobs and rotating wheels, torque is also an effective way for static systems, in other words, systems that are not moving, that are balanced. We use the fact that a non-rotating system would have a net torque as vectors equal to 0. So we're still doing one-dimensional analysis, but in this case our frame of reference is now going to be a clockwise counterclockwise rotation. So if we say going clockwise is positive, then the vector directions for net torque are either positive clockwise or negative counterclockwise. So a system that's balanced, any torque that is causing the system to rotate in a positive way would be balanced out by any torque that is causing the system to rotate in a counterclockwise way, thus yielding a net torque of 0. The most common example is a teeter-totter. A teeter-totter has a fulcrum or a pivot point located at some position in the middle. Generally, we start with a symmetrical problem where this is in the exact center, but it doesn't have to be, and there are obviously many examples of different cases. But you can imagine that if we applied a force on this side, F1, from some distance away, R1, that's your lever arm, as long as this is perpendicular. In order to prevent this system from rotating to the clockwise direction or positively, we would have to apply a force on this side, F2, some radial distance away here, R2, perpendicular to that radius, that would then cause the system to rotate counterclockwise. So we have two competing torques in this case. We have torque 1, which is positive as in clockwise, and torque 2, which as a vector is counterclockwise or negative. So the statement for balance then, as net torques as vectors, would simply be torque 1 minus torque 2 equal to 0. So then magnitude-wise, these two are essentially equal. So we drop the arrows on top and we say torque 1 is balanced by torque 2. Then it's just a matter of substituting in what the radial arms are and then what the forces are, and solving for your unknown. Something important to note for torque balance problems is that if the actual torque bar has mass, which will be defined as a uniform object, uniform objects have mass, have a weight force that's focused at their center of mass. Now for uniform objects, that simply means that they are symmetrical and therefore the center of mass is in the center. But the example here with the teeter-totter is very simple to think about. If we had no attached forces, but the bar itself had weight, if the fulcrum was in the middle, then that weight force that acts here, F of G, creates no torque because the lever arm, the distance from the radius center to the force, is 0. However, if for some reason we were trying to balance the other forces in the system by moving the pivot point, if we move the pivot point, then the weight force from this object is now some radial distance away from the pivot, which means that this will create a torque despite the fact that there are no other forces. And anybody has experienced this because any unbalanced teeter-totter would obviously rotate until this part hit the ground.